Hello, my name is Mark O'Connor and I'm going to take you through a presentation on the structural fire engineering carried out on the Shard. Most buildings are below 60 metres in height in the UK. We as a practice get involved in a lot of tall buildings, and I would say 75% of our work is tall building design, which is greater than 60 metres, which Shard is one example. In terms of the way this presentation is going to pan out, I'll give an introduction to the project and then just go through some of the basic principles. This will be some repetition from what you've seen already, particularly from this morning's sessions, but I just wanted really to put my perspective on it and just bring out a few extra points in terms of how we applied those principles to the Shard. And then I'll then talk about the Shard and what we actually did on that structure and to demonstrate some of the fire engineering techniques that can be used. So just a few facts and figures about the Shard. It's 310 metres high. It says their stories 72, that's occupied stories. The spire on top takes it to 88 types stories high. It was designed by Renzo Piano, and WSP Group were the structural engineer on that project. The services engineer and fire consultant was actually Arab. And the reason why we did the structural fire engineering was that it felt it was more aligned. To have it more aligned towards the structures meant that we can incorporate many more factors into the structural design. So in terms of basic principles, this slide really talks about what happens when fires start to develop in buildings. So what I'm going to plot is temperature against time on this graph. Most fires start small. It's a small initiating event. When that fire initiates, if it's left unchecked, then it can start the temperature in the compartment gets hotter and hotter. As it gets hotter and hotter, more combustibles get involved and the temperature starts to rise. If we reach a point where the radiation in the top layer gets to a certain level, then all the combustibles, and we get a runaway type of runaway failure in terms of temperature rise. And that point is called flashover. And flashover is characterised by a rapid development in temperatures, but after that rapid development phase, then in terms of ventilation and fire load and the actual thermal characteristics of the compartment, you get a steady state burning phase as the fire comes into equilibrium. Then once that fire load is actually burnt out, and obviously we get a decay phase, and this is the way that real fires actually develop. So we just take that plot and start to plot some of the elements of the fire protection strategy on that plot. There are a number of sort of protection measures that can be taken as a fire develops. And the first one is detection. Obviously, we can detect fires before they actually become big enough, then obviously that's got to be preferable in terms of restricting total damage to the structure, and as well as life safety. If the detection is not enough that the fire can still continue to develop, then obviously then we have extra lines of defence in terms of suppression systems, which can actually then come into play to try and control the fire while it's still small. Obviously, in terms of life safety, the thing that kills most people in fires is smoke and toxic products. So obviously, the way we control smoke in terms of ventilation is quite important. Also protected escape routes to allow people to actually get out of the building safely. Another strategy is compartmentation, and obviously one of the things in terms of compartmentation is not only to protect escape routes so people can safely escape the building, but also to try and maintain the fire to the compartment of fire origin. It's only when we have a severe post-flashover fire that structural fire protection then starts to kick in. That structural fire protection is still an important last line of defence, in that if you do get a breach of compartmentation fire, then you don't want a fire starting on the next floor. So that's just really trying to say is that really structural fire protection to start to play a role in the whole fire safety strategy, there has to have been a systemic failure of all the active fire protection measures in that particular building. So let's have a look at the existing design regime. There is obviously a recognition in the code, as we've already seen, that as the size of the height of the building increases, then so does the increased risk. And that increased risk becomes from the fact that we've got more floor area and therefore more risk of initiation. That the time it takes for people to get out of the building is obviously a lot longer. And also the increased difficulty of firefighting in terms of carrying kits up the stairs, etc. And the most common form in most codes around the world to deal with the increasing risk due to height is to increase fire-resistant periods. And obviously that's underpinned by the fire resistance test. And obviously we've already heard in terms of what that test actually involves. And obviously one of the major drawbacks in terms of understanding what happens to real structures in real fires is that that test is only based, it can only test elements of structure. Most of those elements of structure tend to be unrestrained, whereas in real structures there is a lot of restraint to all the main members in the load resistance system. So really what we're trying to say is that the standard fire curve, although it's important for product manufacturers in terms of coming up with a standardised method of characterising their products, it doesn't really tell us a lot about how real buildings are actually going to behave in real fires. And obviously in terms of the regulations, then obviously the prescriptive approach is one way of achieving a certain level of safety, pseudo level of safety, which is unknown. But it's only by carrying out a fire safety engineering approach that we then start to really understand what happens to buildings structurally when they're subjected to severe fire. So in terms of the functional requirements, then obviously they're split into four parts. The first part is to maintain overall stability for a reasonable period. And really for a tall building, what is a reasonable period? Obviously, one is it stands long enough for people to get out of the actual building. That's a given. But in terms of the damage that can be created if we had a failure of a tall building, then obviously it might be never. So really, most tall buildings should really be designed to try and withstand the expected fire load that's actually going to be there in that particular compartment. Obviously, in terms of inhibiting spread of fire, then compartmentation, and particularly the provision of sprinklers, are really important in terms of trying to control the fire. And obviously they're key parts of the actual requirements. So in terms of importance for tall buildings, then the two main points which are important are to maintain stability and compartmentation. So in terms of maintaining overall stability, the main lateral stability of most buildings is really normally provided by core and bracing systems. In terms of vertical stability and the framing arrangements, columns and cores and any transfer structures can be provided at different levels of the structure. So we need to ensure that the failure of key stability elements does not lead to a collapse which is disproportionate to the cause. And in some ways, this is no different to the structural engineer in designing for any other risks which the building may be subjected to. So he's got to ensure that the structure is designed against accidental events. So in terms of fire, what we really need to do is actually systematically assess, first of all, the building to actually establish what the key structural elements are. That is fundamentally important. In the existing prescriptive approach in the building regulations, there is no difference between a transfer structure or a beam carrying just a portion of the floor. And obviously, clearly that can't be sensible in terms of where we actually apply fire protection. So in terms of an assessment, a proper assessment would require identification of the key elements and systems, assessment of potential fire threats in the vicinity, which is mainly based upon occupancy, assessment of worst-case credible fires, assessment of the thermal and structural response of the structure, and then design of the fire protection system to maintain overall stability for that particular building. In terms of compartmentation, compartmentation is an important part of particularly for the design of a tall building, because obviously what we need to do is try and keep the fire on the floor of fire origin. Compartmentation was a key point in some of the major failures, and already you see the building on the bottom right is the Torrey Windsor. In terms of the state of that building at the time it was being refurbished, the actual performance of the building is not really that unexpected. The columns were totally unprotected on the outside of the building. There were major breaches to compartmentation both internally, because there was no fire stop, and in fact that was part of the thing that was being refurbished. So this building here is probably not a good example of a modern designed building in service. It's actually a good example of what happens when a lot of those protection is actually taken away. But one of the key things that's important in terms of maintaining compartmentation is that the deformations you get due to thermal expansion within the structure, there is no real requirement to really understand what the effect of those deformations are on other elements of the compartment strategy. So things like fire stopping and things like partition walls, which are around service risers. There is no real requirements at the moment to actually understand what deflections you're going to get around those areas so that you can ensure that that compartmentation stays in place if there was a severe fire in the building. One of the common misconceptions is that traditionally protected structures also expand. If we consider that you're trying to keep the temperature in a protected member to around about 500 degrees C, and you see a typical unprotected member would get to 1100 degrees C, you can see that the thermal expansion that comes to that protected member is still half the value you would get in a totally unprotected member. So this common misconception that protected structures in themselves do not deflect is basically not true. Also, we have other elements of the structure which are not protected at all, like the slabs, and they will see the same thermal regime whether the structure is protected or unprotected. What they will see is a different strain response within themselves, whether they are protected or unprotected. That is clear. So the use of advanced tools is really the only way of actually trying to understand how a particular floor plate would actually behave when it's subjected to a severe fire. So let's get on back to the shard and try to understand what we did. This is a view of the shard. The shard actually can be split into two parts. One is the tower, which everybody's familiar, but then there's also the backpack, which is an extension of the commercial office area at the bottom, and this is actually the bit that makes the shard actually financially viable. The other thing that's unusual about the shard is that it's a hybrid structure. The basement levels are constructed in reinforced concrete, and the main core that provides the main stability up the height of the building is also a reinforced concrete core. It then transfers to composite steel construction in the office areas to take advantage of the long spans which steel provides, and also the effective integration of services which is required for modern commercial office buildings. For the hotel and residential areas, it then transfers back to a traditional reinforced post-tension flat slab construction. This is because we can get then more floors into this portion of the building. And also that added mass that it provides actually also helps damp down accelerations, which are so important for tall buildings under wind. And then eventually at the top of the building, we transfer back to steel for the spire of the building. The building necessitates various transfers. The column spacings on the outside increase as we go down into the commercial offices, so that necessitates transfers at various parts of the building. Where the tower meets the backpack, we need to transfer columns out to get a better ratio of columns on the commercial office floor plates. So there are various transfers within the building. And that's normal for most tall buildings. What we also have in terms of the fire regime is lots of different occupancies. We have retail at the bottom, then commercial office, and then restaurant, plant, hotel, residential, and then finally the public viewing galleries. So, if you like, there's lots of different fire loads scattered about all up the building. So the main areas to consider. They can be split into basically optimisation of the fire protection requirements to the composite steel systems in the commercial office areas. We did consider the external columns where they come out of the building. Where tall buildings meet the public realm is something which is given particular consideration by architects. On the shard, the columns actually come outside of the building to actually enhance the value of that space. There were miscellaneous compartmentation issues between the different occupancies, which come from Section 20 requirements, which were peculiar to design of buildings in London. And then we had to consider the various transfer structures and how they would actually behave in fire. So we give special attention to those particular structures to make sure the fire protection applied was adequate. We also considered concrete elements of structure in terms of spalling, and then I'll just briefly talk about the spire. So in terms of the main commercial floor plates, obviously, because the building tapers, the floor plates vary in size. But the framing on those floor plates did have some commonality in that we had like double bays or single bay framing arrangements. So what we agreed to do was we agreed with the DS to actually model 3 representative floor plates in terms of determining the fire protection requirements. And in terms of actually calculating the fire to actually apply to the building, we used the parametric time temperature curve to the Eurocode. Now, because the shard is a fully glazed structure, obviously one of the key decisions we have to make is how much of the glass would actually break if we had a severe post-flashover fire, which is what the parametric time temperature curve actually assumes. And obviously that can vary through a series of regimes. So what we do is we consider a range of fires at different ventilation conditions. And basically, if we have a full glazing failure, then what we normally have is a very short hot fire, which burns out within 20 minutes when it gets to a higher temperature. And obviously, in terms of unprotected members, which we do have some, then obviously that will be a worst case fire in terms of the temperature regime applied to that particular element. But also, we have protected elements because we have a hybrid scheme. So obviously, for protected elements, basically the lower the ventilation and the more control the fire is, what actually happens is you get to a lower temperature, maximum temperature, but the fire burns for a lot longer. So what we have is a range of fires which are applied to the actual fire protection on the building. In terms of fire loading, that's codified, and 80% fractile loading of 570 megajoules per metre squared is recommended in the code. But we also did assess sensitivities to a 95% fractile loading just to make sure we don't have any sort of cliff edge events in terms of performance under more severe fire. And then we would develop the FE models, analyse and assess, and obviously carry out some more sensitivity studies in terms of the assumptions we've made within the modelling process. So in terms of what we end up with, this would be a typical fire protected scheme. We would have protected beams between columns. Also, if you look at the service risers around the main core, we would make sure that any steelwork which was used in supporting those critical areas of failure where you could have compartmentation breach, we would make sure that they were protected. All the beams that were protected were 90 minutes fire protected. That was on the basis of a time equivalence type study where we reduced the fire protection required from 120 to 90 minutes, which is a common technique used on most buildings in London. But critically, all columns, because columns are critical elements in terms of vertical stability, and because you don't know how many columns would actually be involved in a fire if there was a severe fire, we actually upped the fire protection requirements to the columns to 120 minutes in this case. And that really was where the majority of, if you like, savings in terms of fire protection was made in terms of the shard. What we also did was we looked at the behaviour of external columns where they came to the bottom of the building. Now, because the columns were at the bottom of the building, those columns were quite large. We're talking about steel plates, which are about 100 mil to 75 mil thick. Also, those columns were actually concrete filled as well for other reasons to do with risk surrounding this particular building. So the approach we took, but these columns were mainly in a sterile compartment. They were either at street level on St Thomas Street or they came down onto the main concourse at London Bridge Station. And obviously the fire load around those areas is virtually non-existent. So the main source of fire loading for these columns was from the office and particularly external flaming from those offices to these columns. Those columns were typically between 5 and 7 metres away from the face of the offices at those particular levels. Now, in terms of the normal design approach for external columns, you would normally look at external flaming calculations, which are in the Eurocodes and also in the PD 7974. Now, in terms of that particular case, there are two normal cases. One is called a through draft case, and one is no through draft case. When you have a through draft case, you assume that you've got maximum ventilation coming into the compartment, and you can get quite long flame lengths coming out of the actual compartment. So therefore, it was difficult to prove that the columns wouldn't become engulfed if we had a through draft case. If we did have a through draft case, then the fire would actually burn for that long. It would burn for 20 minutes maximum, because it would be a fuel control fire rather than a ventilation control fire. So what we did was we assessed the capacity of those columns in an unprotected state under the standard fire curve. And what we did was we calculate we did thermal response calculations under the standard fire curve. We calculate the reduction axial capacity with time. We estimate the realistic time of flame is 20 minutes. So demonstrate that the capacity at 20 minutes is greater than the fire load. Those columns are that large, they've actually got an inherent fire resistance of around about 60 minutes. In terms of compartmentation issues, from Section 20 requirements, that we did have a requirement for 2 hours fire protection at various levels. From a fire severity point of view, no more than 90 minutes was actually required, and that was what was actually provided to these beams. All the beams on these floor plates were protected because, if you notice, we don't have any composite action. These beams are actually protruding through the floor plate and supported on shelf angles. So what we did here was we actually calculated the performance, thermal performance of these members under the standard fire curve, and it was possible to show by doing more capacity calculations that these members in their partially protected state and shielded states would have 120 minutes fire resistance. So let's go on to transfer structures. In terms of designing the transfer structure, what we're really trying to do is calculate the limiting temperature at which these structures will fail. Transfer structures which include inclined members can be particularly susceptible to local heating. And this is because in some ways we don't just get the fire load, the compressive load in those members is not constant. And the reason for that is because if we have one member that's heated or one member that isn't, the one that isn't heated actually provides a great deal of restraint to the one that is being heated. So we have a straightforward restraint to thermal expansion problem. And this can actually be seen in the bottom graph here. This is the axial load in these compression members at the ambient livid state. You see that it's actually in compression of about 4 meganewtons. And what we actually do is we actually heat those members up. And as you can see, as the temperature increases, you can see that the compressive load actually starts to increase in those particular members. If this member was just protected prescriptively to the approved document B, it would assume that the load in that member does not vary. So obviously that is not the case, and this is obviously an unconservative, this is where the prescriptive requirements are actually unconservative. So what we're trying to do is we're actually trying to find the temperature at which that particular transfer system would start to fail. And as Florian said, this value here is the displacement at the top of the transfer structure as it's heated up. So in terms of the structure expanding, you can see that first of all it starts to push the structure up until the system as a whole fails and displacement starts to come down. So obviously what that means for us in terms of fire engineering is that really we need to ensure that under the identified fire scenarios we're going to have for the occupancy in this location, we want to ensure that these members never get above 400 degrees C. And what that actually ends up with is that you actually end up protecting those members with a 2-hour fire protection system. A, because they're critical members within the system, and B, because you actually studied it and understood what the limiting temperature should actually be under that scenario. I won't spend a lot of time on this. Because there was the concrete areas, we also were asked by the DS to actually consider things like spalling. In terms of high-strength concrete, most of the high-strength concrete in the Shard is at the bottom of the building to try and minimise the members down at the bottom of the building. When we get to concrete at the top, then obviously the concrete becomes down to more normal strengths. So what we did was we actually used a qualitative method from the BRE to actually assess where we would actually take any remedial measures in terms of concrete mixes, etc., in terms of reducing spalling. So that was actually considered for this particular structure. Lastly, the spire. I mean, basically, this is quite simple from a fire engineering point of view. It ends up to be an argument by actually looking at what is the fire load within this area. Also, it's what is the ventilation conditions in this area. The spire is really open to the elements. So what that means is that if you had a fire in any of these spaces, first of all, there's no fire load or very little fire load. But if you had a fire in these spaces, then there's really no chance of fire development because it just vents out of the sides of the actual spire. So the chances of getting any kind of localised or compartment type fire area is minimal. And on that basis, the steelwork in that area is unprotected. So, to summarise, again, you can read this afterwards. That is what has actually it resulted in terms of the fire protection study to the Shard. So, just to summarise, I just want to make a few points. Tall buildings normally have usual special structural features which need to be taken into account when we actually design the fire protection system. Not all of those structural elements contribute equally to overall stability and performance of that building in a particular fire. The existing prescriptive design regime doesn't really cater for this because you would just end up applying the same fire protection to all the elements. Therefore, alternative approaches are required to actually demonstrate conformance with the functional requirements. Often this will give rise to a safer building, safer in that you're actually taking into account what are the critical elements of structure, safer in the fact that sometimes you can provide enhanced measures to things like the slab, which are applying compartmentation by identifying areas of high strain and providing additional reinforcement, which you would not maybe do in terms of a prescriptive design. And that's it. Thank you.